All right, so number one, the biggest thing there was that you did not use this equation, constant velocity equation. Like, don't use that. You can't use that because the velocity is changing. You have acceleration, so you needed to use kinematic equation. Then part B, you could do a lot of things. So you would need to figure out how far you traveled in the first 3 seconds, and then figured out how far it went in the last or the additional 20 seconds. You could have used your constant velocity equation at that during the 20-second part. You had a lot of options there, but the big thing there was don't use constant velocity if velocity is changing. Number two, part B, I ask at half the time, are you at half the speed? So there might have been some issues of rounding, but it should have been really stinking close. If you do a velocity versus time graph at half, so here's whatever time that was, 22 seconds, at half the time at 11 seconds, that should be half the change in velocity. Because if you have a constant acceleration, your velocity is changing at a constant rate, so at half the time, you've changed half as much. Good with that? Okay. So just trying to show you different ways to represent that. Number three, I ask a similar question, like at half the time, what is your distance? Distance is not changing at a constant rate. So you at half the time, you're not at half the distance. If you think about it conceptually, you are speeding up, so you start slow, and then as you get faster and faster, you're covering more and more distance. So your position versus time graph would look something like this. And at half the time, let's say this is 6 seconds. So this is how far you ran. At half the time, 3 seconds, you've only run that far. The last 3 seconds, you're running that far. Get that? And you could do the math to verify that as well. Cool. Number 4. This one, I ask at half the distance, what happens to your speed? So this one, it's probably easier just to solve it conceptually, but graphically, position versus time graph is going to look something like this. You needed to make your acceleration negative. If you made the way it's moving positive, which I'd recommend, but you had to make that negative. So at half, so here's your total distance. At half the distance, your time is not half. So when you do a velocity versus time graph, start fast and you go stop at this not half time, less than half. You're still going pretty fast. Okay with that? Okay. And then the last one. part A, I gave you a ton of different, or a lot of information. You could have done this in a lot of different ways. Okay, so you had a lot of choices. Okay? Part B is where it gets a little sticky. So, a very popular error is using 3 seconds. But let me show you why that isn't going to work. Okay? I'm going to throw the gray one. I'm going to drop the tennis ball. Which one's going to hit the ground first? The one that was thrown, right? I mean, that doesn't, you don't have to be in physics to know that. Okay? It had a running head start, just like part B. Had a running head start. Therefore, it wins, which means it spends less than 3 seconds. So you can't use 3 seconds for part B. So you had to use a kinematic equation that does not have time. Good with that? And then part C, that one's usually like wacky. Like which one experienced a greater change in velocity? So this is different than which one's going faster. Okay, the one that's going faster at the end is the one that was thrown. But what I'm asking for is how much change there was. Okay. A experienced a greater change. Why? Because it experienced that acceleration for 3 seconds. Where B experienced that same acceleration for less than 3 seconds. So A experienced a greater change in velocity because it had more opportunity to change its velocity. All right, with that. So watch that between, am I asking for the final velocity or the change in velocity? That's an important distinction. Good? Okay. All right. So give me a confidence rating where we're at.